there's absolutely a requirement for us to try and utilize our finite resources. I still remember going back a few months ago in Germany where they hit a point where they announced that whatever the environment could produce, we had already reached that limit. We're consuming more. So somehow they came up with a metric to measure that this is what's possible in terms of what the actual Earth can produce. And now we've exceeded that as the actual the population as a whole, and it was a pretty scary day for the Germans, and they were really worried about it. However, when we talk about sustainability, this was something that Burkert has already been working on for some time. We've been looking at it from an ecologic perspective, economic and social, and we've actually defined 9 fields of action which are required so that we have these breakthrough goals. So until 2028, we'd like to be 100% carbon neutral. And this is considering scopes 1 and 2. And in addition to that, we're also looking at reducing the carbon footprint of some of the production plants where we're actually producing mass flow controllers and process valves and controls and solenoids and so on. So the presentation today, the discussion that we like to basically deliver is in regards to efficiency improvement, specifically for energy consumption. So today we've seen different perspectives. So this study is purely on energy consumption related to reducing the actual clean utilities, energy required for clean utilities, predominantly for the WFI loop. So we'll just dive right into it. Yep. So the idea is innovation in manufacturing for yield and efficiency improvement. So we're going to review a design and the validation report for water for injection, loop efficiency improvement using standard components for a new improved design. And the next slide, we get to review some of the challenges that we're currently facing. So first, we need to understand the inefficiencies that we're getting in a loop. So once we actually dive into the challenges, we see that at the moment, the point of use can drastically vary, leading to insufficient water for vial washing and manual washing fermentation, also for mixing processes and CIP, which is also brought up by Jerome a little bit earlier today. So now what we're going to do is do the actual comparison using basically hydraulic performance of a WFI and storage distribution system when developed using the standard design, and compare that directly with the new improved design. So the assessment is being performed, developed. It's actually a real life facility that we're using, a biopharma facility, and we're taking a look at their existing WFI distribution network, and we're going to try to see what we can do by using this more improved design. And there's certain aspects that are quite critical that we're going to focus on. And we're going to see if the WFI lines can be reduced, because that's one of the challenges that we currently have. They are significantly oversized, and then that results in very large point of use blocks, flow transmitters, pressure controllers, divert valves, and also oversizing the storage vessel. So sizing it correctly can substantially help with the efficiency and energy reduction, because the loop also needs to be maintained at 85 degrees C, and when we reduce the lines, then less energy is required. Now, this is still going to be in line with maintaining the return velocity of 1.2 meters per second. So we're not going to change anything there. We need to ensure that the ISPE guidelines still need to be followed. And we're going to also address the challenge of course, all the support brackets, everything that's actually being, all the other challenges that are being faced by oversizing the lines. So on the next slide, we can actually take a look at a standard WFI loop. So this study has been done in collaboration with Hyde Engineering from the US. And so in this study, we take a look at the standard existing WFI loop, and the focus is going to be the hot water WFI tank, the pumps, and we're going to also take a look at the heat exchanger, because this is where the energy is being, this is where we actually require the energy. So steam for the heat exchangers, as well as steam for the WFI tank, and then of course the energy which is required for the pumps to be able to move WFI through the actual lines to the points of use, and then returning it back into the storage tank. And as you can see, each one of the actual points of uses has a defined flow rate which is required. And typically we're not able to deliver. We can't promise that the exact flow rate which is needed for the application is being delivered. And lots of additions are being considered, like stroke limiters, for example, on point of use actuators, to see if we can reduce the actual size. But then as soon as multiple different points of use come on, then that calculation is no longer valid anymore. So on the next slide, we're going to take a look at a new concept where we actually have the possibility to deliver exactly the actual flow which is required per point of use by using a quasi-controlled method. And this is, of course, talking about using some of the smart automation technologies that even Mark explained a little bit earlier today, and using that and applying it in a way where we could economically control the actual delivery of the of WFI across each weir by just a very smart method, by delivering just the right amount of air which is needed. So on the next slide, what we can do is we could do the actual calculation for a diversity factor. So we take a look at every POU description. So for CIP skids, for media prep vessels, also for buffer prep vessels, disinfection room, tangential flow filtration systems. As you can see, there's an actual requirement for a flow rate for each one of those uses of the actual media. So for the purpose, there's a flow rate which has been defined, and currently there is no real easy method available to be able to deliver what the actual requirement is. Even the chrome skids have an actual requirement for a flow rate, and typically, if it's absolutely critical, then it's being taken into a buffer vessel and then being dosed in from the buffer vessel. So even the bioreactors, rather than just using directly feed downstream of a POU cooler into the bioreactor, typically there's another stage in between. So to calculate the diversity factor, we've taken the peak demand. So we've taken all the flow rates and determined what is the maximum flow which is required, and that has gotten us a peak demand flow rate of 14.7. Okay, and on the next slide, we see the actual, if we size the blocks correctly using actual KV values and proper hydraulic calculations, we see that there's a big difference between the conventional design and the actual requirement of the weir, which allows you to give the actual flow that we've already defined. So we can see in some of these cases, we're going from 1.5 inches to 3/4 inch. These are some substantial reductions in size, but this is by using proper hydraulic calculations. And it is only possible when you have the ability to be able to modulate the weir and deliver the right amount of flow and make the adjustments, irrespective of how many POUs come on within the limitations of 14.7 meter cube per hour. We know that we're going to be able to deliver the right flow. So the calculations have been done, and there's data available for each one of these weirs to determine that we're going to be operating between 40 to 60% of the actual along the control characteristic curve. And the next slide, we can do the calculations from reducing directly from a 3-inch, and we're going to evaluate 1.5 inch and also a 2-inch to determine and also evaluate the energy which is required, because if we have a lower line size, more energy is required from the pump to be able to deliver the same flow rate, because there's more resistance now. So we'll do the calculations and see which one is actually making sense, what is more efficient. And the benefit that we also see with being able to deliver the exact flow at each point of use, we have the benefit of utilizing a lower safety factor. So typically in a WFI loop, safety factors of 30%, maybe 35% are being considered, when realistically only 5% is actually needed. Okay, so when we go on to the next slide, we see the actual pump sizing as well over here. In this case, we've considered Alpha Laval LKH 10 pump for the conventional system. This is what's currently being used, and we see the actual power consumption is 2.9 kilowatts. But when we reduce the line size to 1.5 inch header, there's a massive increase in power, 8.8 kilowatts, which is just not, not so feasible. But when we take a look at a 2-inch with using the correct safety factor, we're seeing 2.9 kilowatts. So the same level of energy is actually required to be able to deliver the flow which is needed for this WFI loop, reducing it from 3-inch to a 2-inch. And now the storage tank. Yep, and the storage tank, this is a good illustration as well, because we're using what's called a turnaround time, which means the amount of water coming in, how much is available for the next run. So within we need to make sure we maintain a ratio. And based on our study, we used a factor of 1.7. And as you can see, even on the conventional design, so what's currently being used is a tank which has 11,000 liter capacity, which is required, but to maintain the same ratio with the new design, with the 2-inch header, it's reducing to 5,000 liters. Okay. And we also have to make sure that we also look at the heat exchanger. So heat exchanger reduction is also possible now. So to go from a 3-inch size, we have the possibility to go to a 2-inch, and then all the calculations have been completed to ensure that still we're able to first of all reach the sanitization temperature of 121 degrees, and also maintain 85 degrees C in the loop with a lot of buffer, which is being considered, and the same sort of buffer is being used as it would have been for the 3-inch line size. And if we go into the next slide, what we see is this is a summary of what we can expect. So these are purely based on calculations in terms of exactly what would be required, and has also been validated on site for sanitization and normal operation. So the actual plan steam which is required. So first we did the actual exchanger duty cycle in kilowatts for sanitization. So we see that in the conventional design, 124 kilowatts are required, which then leads to 211 kilograms per hour of steam. And as you can see, just for sanitization, when we take a look at the actual improved design with the 2-inch line, we see 101.1 kilograms per hour of steam. So we see immediately, just for sanitization alone, we see that we're reducing energy by less than half. And when we take a look at normal operation, and we have to keep in mind, this is really, these plants are running 24/7. I mean, the only time it's down is when you're maybe making some repairs, maybe you have some downtime after sanitization. I mean, some only a few days that are being considered for downtime. With the exception of that, the plants have to run 24/7 because this is WFI. As soon as the flow stops, I mean, it's no longer possible to use that in the process, because you start with the bioburden, the biofilm, and so on. And when we take a look at the standard normal operation, we see that the plant steam required for normal operation is 90.2 kilograms per hour, in comparison to which can just be 43.7. So also you can see a substantial reduction over there. And this is basically, these are the factors what we're going to use in later slides which are to come. So this is the new hot water WFI loop design with a 2-inch. So what we've added are reduced blocks, so we're able to maintain the exact flow rates which are required, irrespective of how many point of uses come on. So at any, if one is coming on, then no problem, we're able to deliver. For example, if we take a look at the bioreactor room 2, a flow rate of say 500 liter per hour is required, whether just that one point of use comes on, or if you turn on another point of use at the bottom of the actual loop where we have media prep vessels, where only 2,000 liters per hour required. So irrespective of the cycles, we are still able to maintain the exact. Yes, so at the moment, we do see a major shift and evaluation towards digital technologies to be used directly at the level 0 or level 1. So we're going from OT to IT, where we have cyclic data, which is typical, being used with all sorts of different digital communication, but now we have acyclic data as well. And then, for diagnostics, for engineering purposes, and then, all this information which can be stored directly on a cloud through Azure and all different types of method. Google Cloud services are also available. So, I mean, we're certainly seeing a shift where all this information which is available on simple instruments, now with digital technology, we have really the possibility to store and use it for not just diagnostics, but also for trying to reproduce the same batch. For example, if we see that something's working really well with the system, I mean, and it's always going to be different from plant to plant. But if we see, for example, where Mark has actually presented that depending on the source water supply, you need to basically make minor adjustments. And if you find that these minor adjustments are giving you the efficiency of 92% with digital information that you're getting from the instruments, you have the possibility to reproduce that. But first, you need big data to accumulate everything and then do the diagnosis and do the actual, the evaluation. And absolutely, this can be reproduced.